We're here at class 27, talking about the next chapter for Physics 200, spring of 2020, the year of the COVID virus. I assume you've all seen this IOGD, and I hope you've been told that this stands for in everything you do, God should be glorified, which is a kind of a part of Benedict's rule, and of course it's also from 1 Peter. So in particular, all your schoolwork should be in part to the glorification of God. Okay, what is this about? So we got a new chapter, so we've got a new kind of list of objectives. The ones we're going to be talking about today are mostly these guys that have to do with the phenomena of induction, and that's all pretty much in this equation. And of course, the main event in this equation is the magnetic flux, which we've previously talked about, right? So it's kind of how much magnetic field is going through an area. And this is the definition when the magnetic field is constant, but more generally, if the magnetic field varies over the surface area of the loop, then we would have to do that integral. Now, as a matter of fact, what we're going to be spending a whole lot of time on is this minus sign, and what that means and kind of how that goes around. Okay, so this whole process is magnetic induction. It's how changing magnetic fields create electric fields. The last part of this chapter deals with what is really the key idea of this whole course, and that is what are called Maxwell's equations. And several of these equations we've already seen, right? So this is Gauss's law, that if you look at the total electric flux, you get the enclosed charge divided by epsilon naught. This is that there is nothing like a magnetic monopole, something where the magnetic field goes out in all directions. So as much flux goes into a volume as has to leave the volume. And this equation here is Ampere's law, except it's got a new term. And this new term is called the displacement current. And this equation here is the same thing as induction. Okay, so it's kind of a look ahead. What we're talking about today is induction, the fact that changing magnetic fields create electric fields. Okay. What do I mean by this? So here's kind of a typical example. We've got a coil here. And so here's, oops, I've got to have something turned on. So here's a coil, and it's in a magnetic field. And of course, remember that the magnetic field goes from North Pole to South Pole. And if this coil just sits there, there's not going to be any current that's flowing. But if we change the magnetic field, so if we say increase the magnetic field, there will be a voltage that's induced. That is, say, if possible, current will flow through that coil. And not only would this happen if we change the magnetic field, but if we physically remove the coil from the magnetic field so that the flux that coil experiences is less, there would also be a magnetic field. So the main point here is that the magnetic flux, right, which approximately speaking is the area times the magnetic field times the cosine of the angle between them. And in this particular case, you can see the magnetic field is perpendicular to the coil. So the angle between them is 0, and the cosine of them would be 1. The claim then is that the change in the magnetic flux with respect to time is going to cause an EMF, a voltage. And as I said, that could happen by either having the magnetic field change or having the area that experiences that magnetic field change, right? If I partially remove that coil, now the flux is only going to be half as much because only half of the area is going to be so exposed. So the other factor that comes into this equation, and it's, take it or leave it sort of thing. So we could either talk about the total flux of all of these loops together, or we could talk about the flux through one loop, and then here clearly there are 1, 2, 3, there are 4 separate turns. So in general, there would be an overall factor of the number of turns that we would have in this magnetic field. So in the end, what we've got is that the induced voltage is going to be n times the time rate of change, that's supposed to be a d, the time rate of change in the magnetic flux. And then, as I said, most of this talk is going to have to do with that minus sign. And that minus sign is, to some extent unimportant in the sense that usually you're interested in the magnitude of the voltage and not its particular direction, although, sometimes you want one, sometimes you want the other. So it's kind of a long story to get what that minus sign means, and there are kind of 2 ways to go about it, and we're going to start with directly talking about that sign. And this is going to be kind of a long and confusing story. In the end, there's a simpler way of getting it, which is called Lenz's law. But I think the book starts at least by carefully describing why that sign is there, and then in the end we get around to kind of a simpler way of thinking about it. Okay, so to define a flux, we need an area vector, and if you just have a circuit that's sitting there, there's no reason to prefer that vector to one that's going down, right? They're perfectly good perpendiculars to that surface. And of course, if you calculate the flux, if you reverse the direction of the area, it's going to reverse the direction of the flux, the sign of the flux. So the thing that's going to be affected by this choice is the sign of the flux. And it's arbitrary. That is to say, you can choose it any way you want, but once you've chosen it, there are going to be consequences. So this should be kind of familiar to you from Kirchhoff's laws, right? So you had to put those little arrows in the circuit that indicated which way the current was flowing, but which way you put the arrow was arbitrary. And in the end, if you got a negative value for that current, it just meant the current was actually going the other way. So that's exactly what's going to be going on here. Which direction we define as the area, the direction of the area is arbitrary. You can choose it any way you want. And if in fact the voltage is going the opposite way that we might think, then we're just going to get a minus sign for it. Okay, so let's kind of see how this works. Let's get rid of this version of it. So what the problem is supposing is that we have chosen the area vector up, and once you do that, then apply the right-hand rule. And if you apply the right-hand rule, put your thumb in the direction of that area vector, which you arbitrarily chose, then this is the direction that is going to be positive. The direction in which your fingers are curling defines the definition of positive. So the cosine of the angle between the magnetic field and the area is, 45 degrees or something like that. In any case, cosine is positive there. So under these circumstances, the flux is greater than 0. And since that magnetic field is increasing, the change in the flux with respect to time is positive, right? So the flux was, say, 6, and now it's 7. So it's increasing with respect to time. And what the overall equation says is the induced EMF is minus the number of turns, which is clearly 1 in this case, the change in the magnetic flux with respect to time. So what we've seen in this particular case is this is positive. So in the end, the electric field is negative, the EMF is negative, and that means that the EMF is in the opposite direction that we chose when we put our thumb up. Okay, so what would happen? Let's kind of review the same story if we chose arbitrarily the magnetic field going the other way. So if I chose the area vector down, a pure choice, then if I curled my fingers around, what I would have is that this direction would be the positive direction for going around the loop. Now with the area vector down here, the angle between these guys is more than 90 degrees, and so the flux is going to be negative. And it's getting more and more negative. That is to say, it's maybe -6 and it's going to -7. So if we're going from -6 to -7, what that means is that the flux is decreasing with time, right? So if I try and plot that up, if it was -6 and in the future it's -7, the slope of that line is negative. So now when it comes to calculating the time derivative of the flux, we get a negative value, get negative times the positive value, and that means that the predicted value of the voltage is in the same direction as the original arrow. And of course, the voltage is in that direction. What we choose arbitrarily to call the area direction can't affect which way the current would actually end up flowing. Okay, so let's that's one example. Let's go on for more of these examples. Get rid of all of this stuff. I guess I could, well, in fact, why not? I'll just hit delete, start totally again. So what we have here, oops, wrong side. What we have here, oops, not as desired. Can't do that, okay. Oh. Okay, finally. So, so now we have, again, choosing the area vector up, put our thumb in the direction of the area vector, and that defines the direction that we're going to call positive. If we calculate E and get a positive number, then that's going to be the direction that the current is going to flow. If we get a negative value for E, then it's going to point in the opposite direction. Okay, so here I hope you can see that the flux is positive, because the angle between the magnetic field and the area vector is less than 90 degrees. But since the magnetic field is decreasing, the flux is decreasing. So the change in the magnetic field with respect to time is less than 0, right? So in terms of like a graph, we went from this flux to that flux, which has negative values. So when it comes time to calculate the EMF, the time derivative is negative. You can see there's a negative slope, and a negative times a negative is a positive, and that means that the EMF is in the same direction as our arbitrary choice. Now if I choose the normal, boy, I'm clicking on all sorts of things today. If we choose arbitrarily, choose the normal in the other direction, so let's get rid of all that stuff. If I arbitrarily choose the normal in the other direction, so I'm choosing it this way, so now when I put my thumb down and twist my fingers around, now this is the definition of positive. What we have, of course, now is we have a flux that is negative, and it's becoming less and less negative, right? So we have a situation, for example, if we had the flux, it was negative, but it's going to be smaller, going to be, for example, there. So you can see that d phi dt here is positive. So when it comes time to calculate the EMF, we get minus d phi dt. This is positive, we got this negative, so the electric field is going to be in the opposite direction from this arbitrarily chosen direction initially. Okay, boy, I don't know what is causing all of these hassles. Okay, so let's do some more examples. I'm not sure we'll bother reversing these things again. So what we've got here is, again, arbitrarily, we've put our thumbs up, so we've defined the area vector to be going that way, which means that this is the way is going to be defined as positive. So if in the end we get an EMF that is negative, it's going the other way. And you can see that the angle between these guys is more than 90 degrees, so the flux itself is negative, and it's getting more and more negative because the magnetic field is increasing, right? So if we were to kind of graph this up, the flux versus time was here, but now it's going to be even more negative. And you can see that what this means is that the change in flux with respect to time is negative. There's an overall minus sign in the equation. So we got minus minus, we get plus, and so the EMF has to be in the same direction as was chosen by putting our thumbs up. Okay, one last example. So what we've got now is just as before, the flux is negative, but it's getting less and less negative with respect to time, right? So if I were to make a plot of the flux versus time, it's negative, but it's getting more and more small because the magnetic field is decreasing. On the other hand, because we chose thumbs up, this is the direction that is defined as the positive direction. If we calculate the EMF, we're going to get a negative value for it. Because the slope is positive, we've got this negative sign, so the EMF is going to go in the opposite direction. Okay, so that's what this minus sign means technically. In order to have a flux, we have to choose arbitrarily which way the area vector is pointing. There's not a reason to prefer one direction to the other. When we do that, we are automatically getting a direction for current flow through the corresponding wire. If in the end we calculate the EMF and we get a positive number, that means the current will flow in the direction that we got. If we get a negative value, then our fingers are going to, the current will flow in the opposite direction that our fingers were pointing. Okay, so this always seems to me pretty involved, and so I'm at least happy to have an alternative, which has its own hassles, which is called Lenz's law. And what Lenz's law allows us to do is to figure out the direction of the current will flow when we have a changing magnetic field, without going through all of that long argument. And what the rule says is that the magnetic field that the loop is experiencing, the change in that magnetic field what will happen is the current that is induced in the wire will produce a magnetic field which fights the change, is in the opposite direction as the change. Okay, so let me say it again. If the magnetic field isn't changing, there's no induced current, right? Because we have to have a changing flux. If the magnetic field is changing, let's say it's getting bigger, then the induced current will try and make it smaller to maintain the situation. So it's the induced current, except for a superconductor, is not going to achieve the goal of keeping the change from happening. So the change is going to happen, but the induced current is going to fight the change. Okay, so let's see how this works. So in this first example, we've got a north pole, and you know that means that the magnetic field is going away from the north pole. So generally speaking, the magnetic field is going down, and it's getting stronger with time, right? Because the magnet is getting closer. So the induced current will try and fight the change. It will make its own magnetic field that is going up to fight the change. And the way you would make a magnetic field in the coil that's going up would be to have a current that's going around like that, right? Apply the right-hand rule, put your thumb in the direction of that current, and your fingers inside the loop would be pointing up. Okay, so I don't know, maybe this doesn't seem any easier than the other way. So again, the rule is look at the change in the magnetic field that the loop is experiencing. Current will flow in a direction which will fight the change, be in the opposite direction of the change. That is to say, the current will try and maintain the old situation. It won't succeed, but it'll try and do that. What if it's a superconductor? Okay, so now we have a south pole that's moving up. So what this means is that the magnetic field was initially like this, and it's getting weaker, right? Because it's going down. So the magnetic field is falling, and what the current will try and do is to produce its own magnetic field that is fighting the change. It'll try and make a magnetic field that is going up so that the new value of the magnetic field plus its own current is comparable to what it was originally. So the way that you would make the way that this current would make a magnetic field that's going up, again, check the right-hand rule, is by going around the way that it's shown in this diagram. Okay, next example. I'm going to switch over here. So south pole, what we have is a magnetic field that's going up, and because it is approaching, it's getting bigger with time. So the induced current is going to try and make a magnetic field that's in the opposite direction of the change. It's going to try and make a magnetic field that's down in order to try and maintain the old situation. If you put your thumb in the direction of this current, you'll see that it would make a magnetic field that's down, which is what's desired. Okay, last example. So what we've got here is a north pole, so the field is going out away from it, so it's going down, and it's getting weaker because the magnet is going to be further away. So the induced current will try and make a magnetic field that is down to try and maintain the old situation, and see that that is accomplished by having a current that's flowing that way. Okay, so you'll see when you look at the iQuiz questions that there are lots of ways of asking this question and using Lenz's law. So I want to encourage you to take a look at those iQuiz questions, and we'll talk about the solutions to them next time. Okay, so the other topic that we've got is this one about motional EMFs. And it's kind of just another way of thinking about change in flux. So what we've got here is we're thinking about something that is moving. So here I have a hunk of conductor that is moving through a magnetic field, and the magnetic field is going into the page, right? You can see the little X's that indicate that it's going into the page. And just for convenience, let's think about the electrons as having positive charges. It just reverses all of the signs, but it kind of makes things more complicated. So if we have a positive charged particle that is moving this way, remember that the force on it is q v cross b. So if I take the velocity vector, right, which is pointing this way, and I twist it into the magnetic field, which is going into the page, what I get is a force that is driving the positive charge up. And if we're talking electrons, then it would drive electrons down. So the net result is we're going to get an accumulation of positive charge here and an accumulation of negative charge there, which represents a voltage difference. So, and we can figure out the magnitude of that EMF, right, by exactly this result. It's going to be the magnetic field times the length of that section times the corresponding velocity. That's what the voltage is going to need to be to kind of stop this process. Okay, so what we've discovered is there's an EMF, which is going to be the length of this wire, the strength of the magnetic field times the velocity. We can also think about this in terms of kind of changing flux, right? If we have the same bar that is sliding on this device, then the magnetic field here is a constant, but the area is increasing. So the area is, of course, going to be this dimension times this dimension. And this dimension is increasing with velocity v. So the time rate of change in the area is just going to be, I guess I should give this some name. Let me call this L, is going to be L times the change in that horizontal dimension. So the corresponding flux then is going to be LVB, the time rate of change in that flux, and just as before, that's equal to the EMF. Okay, so the main point in all of this is to calculate the induced voltage that happens when we have a changing magnetic field. And I guess what I want to say is that this is how generators actually work, right? So NSP, the electricity company, they have a coil of wire that is experiencing a changing magnetic field, and that's what's producing the voltage that is driving everything in this state. So these are critically important ideas. The kind of generic experiment where we change the magnetic field produces a current, and the kind of complicated story that tells us which way the current is going to flow. At least I find this harder to deal with. And finally, the version which has its own complications, I agree. The idea here is that the induced current is going to try and fight the change in the magnetic field that the loop is experiencing. Okay, so in the next video, we'll see how this pans out for problem-type problems, and perhaps for once I have not gone super overtime. Yeah, we're at a reasonable time frame. Good.